Let's look into the capacitance of a parallel plate capacitor with the dielectric slab. So finally, we are going to put across an expression which tells us by how much, by what factor does a capacitance of a capacitor increase or decrease, actually not decrease, increase only, when we introduce a dielectric slab. So we are trying to study how the ability of holding charge changes when a dielectric material is placed between the plates. So basic idea is we're trying to express capacitance of the capacitor in terms of, say, this area, the distance between the plates, that is D, then thickness of this material T, then the epsilon naught and all of that, and K and all of this, right? The dielectric constant and stuff like that. These are all the terms that we will have end of the expression. Okay, now let's look into the math. So we are considering the same thing, just that a better diagram for your exams. A parallel plate capacitor of area A and the plate separation being D. I think I took that only, yes. With vacuum between its plates, and let the thickness of the, okay, I've not written that. Let T be thickness of dielectric. So the normal diagram that will involve electrical field lines. So that's your E naught, that's your E induced, and that's your net. E induced, or in your books and different places, it's EP also. And this is actually E. I write it as E net. It's convenient for me. Okay. So your derivation starts off recalling few things, starting with capacitance in free space. So we need a benchmark. So let's call it as C naught. So this is epsilon naught A by D, right? And your E naught will be equal to charge density by epsilon naught, if not Q by A epsilon naught. Again, we are just writing the things which we kind of already know of. Now, induced field, that's your EP or E induced. Let's write EP only. The charge density on the plate on the dielectric divided by epsilon naught, if not P by epsilon naught, right? Polarization and stuff. Then we have the net field, right? That's equal to E naught minus EP. E naught is also equal to, sorry, E net is also equal to E naught by K. That's the definition of your permittivity of the material, right, guys? So these are all the things that we have derived, right? So let's move forward. So next is in terms of velocity, not velocity, sorry, voltage. So yeah, we are going to go a bit off track. See, voltage, the entire voltage end to end is equal to voltage in free space, right? It's like connecting things in series. Plus voltage in what? Can you guess? So this is not for your exam. This is for your understanding. If I have two resistors, if this is V1 and this is V2, and your V will be what? V will be equal to V1 plus V2, is it not? And that's all we are doing over here. So the voltage between the plates will be the voltage between the gaps plus the voltage that is existing between your dielectric. That's all. So free space is this empty space. Okay, guys. Plus the voltage in dielectric. So some of you might be having this question that do we or don't we touch the dielectric? We can. It's insulating material, right? We can. So this is equal to what? Voltage is equal to your basic definition, electrical field line, force into displacement, right? In some sense. And over here it is T. Agree? Free space will be the difference between the entire length D minus the thickness of the capacitor. So E into D. And here it is E into T. But there is a small catch. This has to be E naught. And this has to be E. Let me write it neat. E naught. This is D minus T plus E net into T. That's T, right, for us. So yeah, T. Correct. Okay, nothing fancy, just going with the flow. So let's express E net as E naught by K into T, and so V will be equal to, so E naught as per here. Okay, let me take E naught first. Let me not confuse you guys. If I take E naught, I will be left out with D minus T plus T by K. And then substitute E naught from 1. So from 1, just a second guys, I need to make some space. Okay, I got my space now. So from 1, what do we have? So V is equal to E naught is your this expression, right? So charge by area epsilon naught. So D, we're almost there, we're almost done. Minus T plus T by K. So finally, what do we have? So we are going to this particular expression, which expression? C is equal to Q by V. Okay, so if I rearrange over here, so V by Q or Q by V, my bad. If I go with Q by V from this particular expression, what should happen? A epsilon naught should go to the numerator, while the denominator should have T minus T plus T by K. And this is nothing but your capacitance of a capacitor. Simple as that. Okay guys, so now the question, some of you might have asked this, or most of you might have asked this. What happens when we have the entire thing to touch from one end of the plate to the other end? You know, this from here till here, here till here. What will happen? In terms of variable, what will happen? One more clue. In terms of T and D, what will happen? Right. What will happen? T will be equal to T. This implies T is equal to D. Dielectric fills the entire space between the plate. T will be equal to D. And so what will happen? C will be equal to, this two terms will get cancelled. And we have A epsilon naught, not K, I know it's kappa, by T. Right? Okay. Yeah. So T. So that would be your expression. Or we can rewrite this also by D, because T is equal to D times of K. And this is what? This is your C naught. Agree? This is C naught. Sorry. So it will increase by a factor of kappa. Finally, we got our result. It's been a long journey, but it's a very simple expression end of it. It just increases by a factor of kappa. That's it. That's weird, now. So I want to end up this expression also in terms of your C naught. So for that, I'll multiply and divide with D over here. So we'll end up with D C naught D divided by d minus t plus t by k. All I did was I multiplied and divided with d. So a by d epsilon naught will give us what? C naught. So the numerator d will still remain. So basically I did this, guys. Let me light. Yeah. D by d into. So basically this expression gives us C naught and there's a d in the numerator and we end up with this. Again, I wanted to express in terms of C naught. So that's the whole funda. Okay. So with this, we'll be able to redefine dielectric constant. Dielectric constant of a material can be defined as the ratio of the capacitance of a capacitor completely filled with the material to the capacitance of the same capacitor with a vacuum between the plates. Right? Basically, we are expressing this. Okay. So with this, you will be able to redefine your dielectric constant. Again, you can get any question anyhow. We need to be very clear with this.